Hello everyone, welcome to our presentation, QuTE Answering Quantity Queries from Web Tables, proposed by Max Planck Institute for Mathematics. And to start, let me give some motivations about this work. Quantities are financial, physical, and other measures that denote important properties of entities, such as revenue of companies or energy efficiency of cars. Quantities usually appear in quantity queries, which are an important building block for comparative search. For example, we can ask for buildings higher than 1,000 feet or electric cars with price under $30,000. For the query about cars price, a middle search engine will return a list of entities, which is good. However, as you can see, these results are from a single page, and they are usually under a list structure, which is very easy to extract. If we change the query a bit by asking for the price under 29K instead of 30K, then the search engine will return a list of documents. Yeah. The main reason is that the search engine does not really understand the quantity in the query, and instead they treat the query as a normal string. For handling this kind of queries, in our earlier work, we have worked on extracting quantity fact from text. And because our web tables are a rich source of quantities, this is a motivation for us to extend our work to extract quantity facts from web tables and to support answering quantity queries. However, extracting quantity facts in web tables is a difficult task. And why is it difficult? This is an example table about football teams, and here we need to answer several questions. The first question is, what is the unit and the solution of the quantities? You can see that it's very hard to correctly extract quantities in this table because they vary in units even within the same column, like this column. And moreover, the quantity values are also affected by a scaling factor even in the column header. This question has been actually successfully addressed in the earlier works. However, this is only one part of the story. In order to make the quantities meaningful, we also need to answer the other two questions. Which entities does the quantity refer to, and what is the relation between them? For answering these questions, we need to solve a problem which is called column alignment. And the objective of the column alignment task is to link each quantity column to proper entity column so that we can extract quantity facts from the linked column pair. For example, in this table, we want to link the column capacity to stadium and value to team. However, this problem is not easy. About the prior works for column alignment, many papers adopt a very simple heuristic. For example, the first column heuristics links all the quantity columns to the first column of the table. The most unique heuristics links all the quantity columns to the column with the most number of unique values, and the closest left heuristics links each quantity column to the closest entity column on the left. However, these heuristics do not always work for complex tables. Some other prior works assume that there is a single subject column of the table and build a classifier to identify that column. However, this assumption is not always true. That doesn't allow multiple subject columns in the table, like the one we are considering here. There is also another work that allows multiple subject columns by identifying functional dependencies between columns using entropy. But this does not work well for quantities and for small tables, because in these kinds of tables, a common situation is that the values are often unique, and hence the entropy does not really help. The last approach, which is the most prominent one, is to identify the correct column alignment by mapping column pairs to an existing KB relation. However, this approach cannot be directly applied for quantities because we do not have a rich KB of quantities yet. So in this work, we will describe a method that specifically supports extracting quantity facts for web tables, and then we use the extracted facts for answering quantity queries. And now we will describe our approach. The quantity fact model that we use in this work is called QFact, proposed from our earlier work. A QFact is basically a triple of EQX with the KB entity E as a subject, a quantity Q as an object, and a context X, which is basically a bag word that describes the ENQ relation, like a predicate in the standard RDF model. For example, in this table, we want to extract Q facts about team values and about stadium capacities. Here, it is very important to see that the context of a Q fact could come from not only the column header, but also from the outside of the table. For example, the table caption or from the page title. With this computational model, our QFact extraction starts with a table preprocessing phase to detect entities and quantities in the input table. For quantity detection, we use two earlier works. The first one is applied to table cells to identify quantity values and units, and the second one is applied to the column headers to discover an additional unit and scaling factor if available. For entity disambiguation, we adopt a method from the prior work with inference over a probabilistic graphical model. And this is the output of the pre-processing step. You can see that the entities are already recognized and linked to a KB, and the quantities are extracted with a proper value and unit. And now we perform column alignment on this pre-processed table. So our method for column alignment has been recently proposed in the web conference this year. We defined the quality of a column alignment as the average quality of the candidate table QFact generated from it. For example, in this table, we want to compute the average quality of the candidate table QFact from the alignment between column pairs team value and stadium capacity. And here, we estimate the quality of a table QFact by using an external data collection. Prior work on column alignment usually use a KB as the evidence for scoring a candidate table fact. But as we have mentioned before, because we do not have a rich KB of quantities, we have to use a different kind of data. And the kind of data that we used is text corpora. Okay. So our key idea for scoring a candidate table QFact is to retrieve evidence from a large corpus of text. In our early work, we have worked on extracting QFact from text, and now we can make use of this technique to obtain a collection C of QFact from a large corpus of text documents, for example, Wikipedia or news articles. And then we compute the evidence score for a candidate table QFact, EQX, by finding the best match QFact in C with the same entity E. The QFact similarity is basically the combination of quantity similarity and context similarity measured by the two functions sim1 and sim2 here. For example, when estimating the quality of this candidate fact, we find a text snippet, and from this text we can extract an evidence QFact. You can see that both the candidate QFact and the evidence QFact mention about the same information. But this method does not always work because for many candidate table QFact, we may not find any text-based evidence. This is expected because if we can always find the same information in text for any table QFact, then there is no reason to extract fact from tables, and instead we can extract from text only. So our solution for this problem is that apart from looking for evidence with the same entity, we also search for evidence with the same entity type. For example, with the candidate table QFact that we are considering as before, we not only find the exact entity evidence, but also find text snippet about capacity of other stadiums. This is a very strong evidence that when we talk about capacity, it's very likely that we talk about a stadium rather than talking about a team. Okay. So far, we have described our approach for extracting QFact from web tables. And now we would use this extracted QFact for answering quantity queries. An important step after extracting QFact is called QFact contextualization. The problem is that sometimes we cannot fully understand a QFact with only the quantity column header in the QFact context. So in this step, we basically contextualize the QFact with not only the quantity column header, but also with other components of the table. For example, the table caption, the cells on the same row, the page title, DOM tree headings, and the text surrounding the table. These components are weighted and combined together into a bag of words. For query processing, given an input quantity query, we first decompose the query into a triple of entity type, quantity condition, and query context. And then for each QFact EQX that we have extracted from web tables before, we perform three kinds of matching. Entity type matching using the type information of the entity from the KB. Quantity matching, checking if the quantity of the QFact satisfies the quantity condition of the query. And then, if the QFact passes these two filters, we perform the context matching and compute a relevant score for it by using our proposed measure, which is called weighted directed emitting distance. And finally, we further improve the ranking of QFact through a corroboration step by considering the mutual consistency between the answers. This produces the final QFact ranking and returns the results to the user. Due to time constraint, we refer to our original paper for more detail about these steps. And now for the demonstration. Our system QuTE runs on a collection of web tables compiled from two datasets. The English Wikipedia with total of 1.8 million tables and the table L dataset from the earlier work with total of 2.6 million web tables. The QFact extraction step produces total of 18 million QFact with information about total of 800,000 unique entities. Our demonstration system is available from the link in this slide, and now let's explore it together. This is the main page of our search system QuTE. Here, users can type the input quantity query into this search bar using telegraphic phrases or full-fledged questions. While users are typing their query, the type succession feature will give hints about what kinds of data that are currently available in the search system. And now, let's try one example query, buildings higher than 700 feet. Here we are. This is the result page. As you can see, the input query is decomposed into the triple of entity type, query context, and quantity condition, which is further decomposed into a resolution code, a value, and a unit. Here, we show top entity results ranked by their relevance to the query and along with the table from which the results are extracted. We use different colors to highlight different parts of the answers, including the answer entity, which is in light green, the answer quantity, which is in red, the answer context, which is in gray, and other components of the table, if available, such as the page title, the DOM tree headings, the table caption, and the text surrounding the table. More importantly, for the answer quantity, if the unit of the answers is different from the one being asked in the query, we also provide a conversion in a zero box. By default, we show only the highest scoring QFact for each entity. However, we can click on the Show More button to display more QFacts for the same entity, which is extracted from different tables. Here, the answers from QuTE are ranked by their confidence score. However, we can also re-rank them in ascending or descending order of the quantity value, or by the prominence of the entities. We can do this by using this Sort By button. These secondary rankings only affect the top answers from the result page. Next to each entity annotation, there is an evidence link, and by clicking on it, we can obtain explanations and additional information about the QFact answers that are extracted from text document. Here, we show evidence sentences of two types, exact entity evidence, and type lifted evidence, like what we have described before. Now, about the search settings. We allow the users to customize the search by using a settings box in the top right corner of the page. Here, users can customize the input table corpora, the number of results on each page, the alignment threshold value, and the corroboration step by using interfact consistency learning. Due to time constraint, we refer to our original paper for more details about these options. And now, let's try a few other questions to see how the results from our search system look like. Let's change the current query a little by asking for Asian buildings higher than 700 feet. You can see that we have no result for this query, even though the query is correctly parsed. One reason for this is that the type information in our KB does not include the type Asian building. So, to solve this problem, we provide users with a secondary search mode by clicking on this toggle button. In this search mode, users can provide more concrete information need with the three components of the input query, including the entity type, the query context, and the quantity condition. For example, we can relax the query about Asian building by including the keyword Asian into the query context. The results are quite good. You can see that the search system can capture the context token Asia from the different parts of the table, like in the same row cell or in the page title. Now, let's try another question about sprinters who run 100 meters under 9.9 seconds. Similarly as before, our search system can also capture the context token 100 meters appearing in the table caption. Or in the page title. Let's make the query harder by adding a time constraint into the query by asking for sprinters who run 100 meters under 9.9 seconds in 2019. You can see that our search system can also capture the context token 2019 from a same row cell or in the page title. However, you can also see that there is still some limitation of our search system. For example, the result at rank 3 is wrong, and its reference time is in 2009, not 2019. Or in the result at rank 6, the running time is for the race of 60 meters, not 100 meters. A running time of about 8 seconds for the race of 100 meters is quite unrealistic. These are few open issues that could be addressed in the future. We would like to conclude our paper here. In this paper, we have built an end-to-end QA system for answering QuantE queries based on data from web tables. The novelty of our approach is a new method for extracting quantity facts from web tables using evidence from text. Finally, you always can try our system at the below link. Thank you so much for listening.